Forces 1, Newton's laws of motion. So Isaac Newton published a very famous book, Principia, one of the most important books ever written, and in it was his 3 laws of motion, Newton's 3 laws of motion. He didn't come up with it all. A lot of it was building on the work of other people like Kepler and particularly Galileo, but Newton brought it all together. His 3 laws of motion, very, very important. Without it, there wouldn't have been an industrial revolution. So, what are Newton's laws of motion? Newton's first law: a body will remain in a state of rest or unaccelerated motion unless acted upon by an external resultant force. Basically, if there is no resultant force acting on an object, resultant as in if you add up all the external forces acting on it and you get 0, so there's no resultant force acting on it, then it's going to be stationary, it's not moving. We say it's in static equilibrium if it's not moving, or it will be traveling with constant velocity, which is a dynamic equilibrium. So basically, if all the forces acting on an object add up to 0, then it's not accelerating. Okay, here's some examples. The most obvious one is the cup on the table. There's the weight of the cup downwards, there's a normal contact force upwards, the forces are equal and opposite, it's not moving. All of these are actually static equilibrium. There's the block resting on a slope with friction stopping it sliding down. There's a ladder leaning against a wall. There's a picture hanging on a wall. There is no resultant force acting on any of them because they're in static equilibrium. A few notes: the weight of an object acts from the center of mass and it is towards the center of the earth. Normal contact forces are perpendicular to the surface. I mean, that's what the word normal means. Normal means perpendicular. And friction will always tend to oppose motion. If you look at the object and you think, well, which way does it want to move, then friction will be in the opposite direction. Okay. For AQA, you also need to know about moments as well. If an object's in equilibrium, then there's no resultant moment. At OCR, we don't do moments. These objects are in a dynamic equilibrium, and again, all the forces on them will cancel. There's no resultant force. The car driving along, the parachute coming down, the guy skiing down the slope. Again, friction is opposing motion. Friction is opposite to the direction that it's moving. And resistive forces, including drag. If an object moves through a fluid, then a type of friction is the resistive forces as it moves through the fluid, and also friction between surfaces rubbing together. Okay, and these resistive forces increase with speed, which is why all of these objects would reach a terminal velocity. Newton's second law of motion is basically if there is a resultant force, if the object isn't in equilibrium. Now, if you haven't looked at momentum yet, well, technically it's the rate of change of momentum is directly proportional to the resultant force and in the same direction. Now, I'm not going to dwell on this now, but basically F equals ma. F equals ma isn't Newton's second law, but it's from Newton's second law. It's from F is proportional to dmv dt. But basically, F equals ma comes from Newton's second law. And the definition of a Newton, 1 Newton is the force needed to give a mass of 1 kilogram an acceleration of 1 meter per second squared. That comes from F equals ma. Here's a couple of questions you can have a go at. First one's very straightforward. Be careful with the second one. I'll show you the answer in a couple of seconds, and it is that. Here's another couple of questions for you to have a go at. Be careful, again, they're perhaps not as straightforward as you might think they are at first. Have a go at them, and the answers are that. Newton's third law. For every action there is an equal and opposite reaction. I personally think that's a bit vague. I much prefer if a body A exerts a force on body B, then body B will exert an equal and opposite force on body A. Forces come in equal and opposite pairs. Every force has an equal and opposite force somewhere. Okay. Examples of that, again, there's the cup on the table. There's the tension on this climber is equal and opposite to the climber's weight. This is why we'll talk about momentum later, but things like cannons and rifles, there's a recoil as it pushes the cannonball forward, the cannon is pushed backwards, and that's not me on the bulwarker. Okay, here's another couple of examples. The Earth and the Moon attract each other gravitationally, and the force is the same from Newton's third law. The alpha particle being emitted by the nucleus recoils as it is emitted. If you want to go forward in a canoe, what you do is you push water in the opposite direction to the way that you want to go, and then the water will push you forward. And the principle behind propulsion, as in a rocket, any vehicle propulsion, is from Newton's third law. Here's a question you might want to think about. An astronaut, Sandra Bullock, is adrift in space after her jetpack ran out of fuel. She must think of a way of getting back to the spaceship soon before she runs out of oxygen. Can you give her advice based on the physics that you know? So you would say from Newton's third law, if she takes off her jetpack and pushes it in the opposite direction to the way that she wants to go, there'll be an equal and opposite force on her. She will accelerate towards the spaceship and get there just in time and survive.